Professor at the University of Illinois. It's my pleasure to introduce the session. The first paper is from people from ETH and from ETH Zurich and from Intel. And the presenter will be Rahul Bera. Rahul is a fifth-year PhD student working with Professor Onur Mutlu. His research interests are microarchitecture and memory system design, with an emphasis on data-driven microarchitecture. Rahul?
Can I have the feed from? Mitigate this resource dependence. We found out that if we ideally eliminate all such global stable loads, meaning mitigating both their data as well as resource dependence, it has 9.1% performance headroom as compared to only 4.3% performance headroom if we only ideally value predict the same global stable load. So this clearly shows that if we mitigate both the data as well as resource dependence of these global stable loads, they have twice more performance headroom left than just only value predicting these loads. And in fact, if we see the ideal eliminations performance, it even exceeds the performance of a processor that has twice more load execution capability. Now, as we have seen in the past a decade of processor design, that the execution resource scaling, load execution resource scaling has traditionally lagged behind the scaling of other pipeline resources due to its inherent area and power limitations. We believe that the performance potential coming from mitigating load resource dependence is going to be even higher in future generation processors. Thus, the goal of our work is to improve instruction-level parallelism by not only mitigating load data dependence, but also mitigating load resource dependence. And towards this, we propose Constable, which is a purely microarchitectural technique that mitigates both load data as well as resource dependence by safely eliminating the entire execution of a load instruction. Now, Constable is based on a very simple key insight that if there are two successive dynamic instances of the same load instruction, Let's call it LD1 and LD2. Then if the source register of this instruction has not changed in between these two dynamic occurrences, then LD2 would have had the same address as LD1, which means that the address generation of LD2 can be safely eliminated. Similarly, if no store or snoop request has arrived to the address of this instruction in between these two occurrences, then that means that LD2 is guaranteed to fetch the same data also as LD1, which means that data fetching operation of LD2 can also be eliminated. So Constable exploits this key insight to work on two key steps. First, it dynamically identifies load instructions that have a history of fetching the same data from the same address. And second, once it identifies those loads, it simply eliminates their execution by tracking modification to their source registers as well as load addresses. Now you might be thinking that, okay, the skipping redundant computations by memoizing previously computed results is not new. And it has been actually explored extensively in the past in literature. Now these works often aim to memorize multiple dynamic instances of every single instruction in the program, and they often require large memoization buffer which exceeds even the size of the L1 data cache. Now Constable improves upon these prior works in three key ways. First, Constable focuses on loads and only to those loads that have been proven to be likely stable. So this significantly reduces Constable's storage overhead as well as its design complexity. Second, unlike prior works that requires the source register of an instruction to be available before it can eliminate a load instruction, Constable eliminates a load instruction much early in the pipeline at the rename stage by explicitly tracking the modifications to their source registers. And third, Constable ensures correctness even in today's high-performance processor that implements multiple performance enhancement techniques like out-of-order load issue, multi-core or multi-threaded execution. Now let me give you a brief design overview of Constable. So as I said, Constable has two key steps. It identifies the likely stable load and then eliminates them. Now let's see how Constable identifies likely stable load. So for identification, Constable uses a stability confidence counter per load instruction that essentially measures how frequently this load has been fetching the same data from the same address. Now once the load execution finishes, if the data and the address matches with the previous dynamic instance, it simply increments the counter, or if it doesn't match, then it simply halves the counter. Now once the stability confidence reaches a specific threshold, then Constable simply starts tracking the source register and the last executed address of this instruction in two separate hardware structures. It remembers what was the last executed load value of this instruction and sets a flag that we call eliminate flag. Now setting this flag essentially means that any subsequent instance of this instruction can be eliminated from now on. So whenever a new instance of this instruction comes in, Constable simply looks up the elimination table, sees that the eliminate flag is on, so it simply eliminates its execution. By eliminating execution, we mean that no reservation station, address generation unit, and load port would be assigned for this instruction, and its data dependence is going to be broken using the last value of this load instruction. Now, keep this in mind that these eliminated load is still going to take the reorder buffer and the load buffer entry to maintain the correct elimination of any in-flight loads that are still there in the pipeline, which we have described in detail in the paper. If you're interested, then you can take a look at it. So now, as long as this eliminate flag stays on, Constable simply keeps on eliminating further instances of this load instruction again and again. Now, let's say one instruction comes in that either modifies any tracked register or the tracked addresses. Constable simply looks up the corresponding monitor table, resets the can eliminate flag of the load instruction. Now, resetting this flag essentially means that any further instance of this instruction should now be executed from now on. Now, once this instruction finishes its execution, it's going to update the stability confidence accordingly, which again needs to be regained before this instruction can be eligible again for the elimination in the future. Now, in the paper, we have mentioned many more details of Constable design. For example, how it ensures correct elimination in presence of out-of-order load issue, multi-threaded and multi-core executions, how do we integrate Constable in the entire processor pipeline, as well as microarchitecture for breaking the data dependence, and its own structures, which you can find in the paper. Now, let me just quickly evaluate Constable. So for our evaluation, we use an industry-grade, cycle-accurate simulator that models a very aggressive out-of-order processor that already has memory renaming and multiple dynamic instruction elimination strategies in the baseline. We have used 90 workloads of wide variety of spec CPU, client, enterprise, and server applications to evaluate our work. And we have evaluated Constable against 3 prior state-of-the-art techniques in both the 2-way SMT and no SMT configuration. But for the sake of today's talk, I'm going to focus on comparing Constable against the state-of-the-art load value predictor called EVES. So let's see how the performance improvement looks like in a no SMT system. So this is how the performance looks like for a no SMT system by Constable, as well as the state-of-the-art load value predictor Eves on top of a strong baseline. So the first key takeaway is that Constable by itself provides nearly same performance benefit as Eves while having half of its storage overhead. Now, if we add Constable on top of Eves, that provides 3.4% more performance benefit on top of Eves alone. Now, in the two-way SMT configuration, where the resource constraint is even more severe, we see that Constable by itself provides 8.8% performance, and if we add Constable on top of Eves, then it provides 11.3% performance benefit. Now, let's see how Constable improves the resource efficiency of the system. So as the eliminated load do not access the L1 data cache, we observe a 26% reduction in the L1 data cache accesses. And similar to the L1 data cache, we also observe an 8.8% reduction in the reservation station allocation, since the eliminated loads do not also take reservation stations. Now, this improvement in resource efficiency gets directly translated to the improvement in dynamic power. So here I'm showing the memory execution unit power broken down into key components like L1 data cache and data TLB. So as you can see here, that unlike the load value predictor Eves, Constable actually reduces the power of the L1 data cache by 9.1%. Similar to the memory execution unit, I'm also showing there the power of out-of-order unit broken down into reservation station, register alias table, and reorder buffer. And as you can see, Constable also reduces the power consumed by reservation station by 5.1% on average. Now, all of this benefit comes at a very modest overhead in the storage, as well as in the area of the processor floor plan. Now, we have many more exciting results in the paper, like, for example, how much loads are getting eliminated at runtime, workload-wise performance analysis, as well as a wide range of sensitivity study on processor parameters, which you can find in the paper. So now let me summarize the entire thing. So I want you to take the 3 key takeaways from this presentation in the end. First, a large fraction of the load instructions are fetching the same data from the same address throughout the entire workload, even after aggressive compiler optimization. We call such loads global stable, and we found out that these global stable loads, even after having load value prediction and memory renaming, they have resource dependence left in the system, which provides even twice X more performance headroom than just breaking their data dependency by any of the prior works. So this motivated us to design Constable, which we showed to provide high performance benefit while improving resource efficiency and dynamic power, all while consuming only a modest storage overhead. Now, we still believe that there is a lot of performance headroom still left. On average, we are only seeing the 57% of all the global stable loads that we identify offline are getting eliminated at runtime. So thus, we believe that we still need to understand these loads. Why do they even occur in the program even more? To aid this process, we have released an open source binary instrumentation tool that we call Load Inspector, which you can download from our GitHub repository. You can use this tool to study global stable loads present in any of the shell x86 program, as well as you can use it to study the effect of increasing architectural registers using the recently released Intel APX extension to the x86-64 ISA. With that said, I'll be concluding my talk here, and I'll be happy to take questions.
Thank you, Raul. Okay, so please ask questions now. Say your name and affiliation, please.
Hi, this is Cleo from Huawei Research Zurich. Thanks a lot, great work. Loved it.
Thank you, Cleo.
I just wanted to ask 2 things maybe. Like first, to pick up your brain, if you want to tell us, like if you find something like specifically, like as you say, around more than 30% of loads can be eliminated, right? Mm-hmm. So compiler doesn't get that, I guess, because I've seen that as well for value prediction. So do you see like any particular, let's say, reason on workload-based analysis, like why this happens? And then second, maybe just to quickly say, it's like that in the design, like, for comparing with value prediction or with similar techniques, except from the fact that you are actually eliminating, which is like the basic thing, right? So what is then the fundamental, let's say, difference on tracking the behavior? Like how can we, is there something specifically different on compared to value prediction, how we identify this? Like for example, do you train at speculative path?
Can we keep the question short, please, because there are many people around there.
can I go to this presentation slides maybe to answer the first question? Yeah, sure. So I'm going to show one quick example of why compiler is failing to optimize these loads, right? So here is one example. Let's say this is a singleton variable of srandom, right? And we have the access function for this variable, right? Now, if you see the disassembly of this code, right, what I want you to focus on is this if function, right? So what this if does, it loads this srng variable from the memory and just simply test it. Now, the fact is that this variable, by the virtue of how we write program, it's going to be stable. Once we initialize it in the beginning, it never changes, right? So by virtue of that, it's going to be global stable. But for compiler to eliminate this load, it needs to reserve a register throughout the entire scope of the program, and compiler never does that. So even if we have enormous, gigantic number of ISA registers, like architectural registers, it may still fail to eliminate such loads. And we know that these loads exist. And that's just one example. I have another examples also which I can tackle. And the second question to answer your question is that the fundamental difference between tracking a load for Constable's target and a load for value prediction may not necessarily identify the loads going to the same address. So Constable is more focused on that part. So it needs to have same address as well as same data. That's one thing. And the second thing is value predictor like Eves, it may not also need to have the same value repeated. It can have the stride in the value. So in a sense that the targets for Eves is much higher for optimization, but Constable only focuses on the ones that have repeatedly faced the same value, same data. So that's how the tracking difference is.
Okay, very good. No, let's move on to the next question. One more question only, please. One more. Sorry about this. One more. Just one more.
Hi, my name is Vignan. I'm from Tenstorrent. I want to ask if you limit the savings to just the load port, do you know what is the benefit we get? Because some of the load queue allocation in some of the architectures happens later after dispatch or after issuing the load to the load store unit.
So the ideal elimination headroom that we showed, right, it's coming from eliminating load ports as well as the reservation station.
Right.
So you want it to be specifically for the load port.
Just the data port for the caches.
I see. Yeah, so we haven't actually specifically done what's the coming from that load port itself. Okay. But yeah, I mean, that's the headroom that you can get if you eliminate all of them, right? So
I agree. Yeah. Just trying to see if you had any.
Good question. Yeah. I guess if there are no questions, then...
No, wait a second. Okay. Let's thank the speaker again.
Thank you very much.
Already, the second talk is from Argonne National Labs and North Carolina State University. The speaker is Zain Hamid Saleem. He's an assistant scientist at the Argonne National Lab. He works on quantum computing and quantum sensing, and he has been recently focusing on quantum error mitigation. Zain, go ahead.
Hi, so my talk is on quantum error mitigation, and I'll be talking about this QuTracer framework that helps mitigate errors, gate errors, and measurement errors by tracing subset of qubits. So as we know, we are in the NISQ era right now, and we don't have fault-tolerant quantum computers. So in the absence of fault tolerance, quantum error mitigation has emerged as a promising strategy to deal with errors arising during quantum computation. Instead of fully correcting the errors, we mitigate these errors to an acceptable level, and QuTracer is a framework that mitigates both gate and measurement errors. Okay. So there are three important components of QuTracer: measurement subsetting, quantum circuit cutting, and polycheck sandwiching. They work together synergistically in the entire QuTracer framework to do the gate and measurement errors, to mitigate the gate and measurement errors. So measurement subsetting is you measure a subset of qubits instead of all the qubits together to avoid qubit measurement crosstalk. Quantum circuit cutting is a technique that allows large quantum circuits to be broken into smaller fragments that can be run on then smaller devices. And then classical post-processing can be used to combine the results and get the result from these fragments of the total circuit. Polycheck sandwiching is an error mitigation scheme that uses pairs of polychecks that sandwich the payload circuit to detect errors via a post-selection mechanism. I'll go one by one over the three components now. So first is measurement subsetting framework. There's Jigsaw and Warsaw. What you do is you get a noisy global distribution, then you do measurement subsetting where you just choose a subset of qubits and get these results. Then by a Bayesian recombination, you basically get the global error-mitigated global distribution. The quantum circuit cutting works by measuring complete basis sets on the left side of the cut and preparing corresponding states on the right side of the cut. The downside of circuit cutting is that it's exponential in the number of cuts, but if you cut few qubits, the cost is not that bad. In this present QuTracer framework, we will track the state during circuit execution, and we will repurpose the circuit cutting technique. We won't fragment the circuits. We'll just use these as sort of quantum watch points, similar to like watch points when debugging a classical program. The third component of QuTracer framework is polycheck sandwiching. What you basically do is you ask the circuit to obey certain constraints. Here, CLU, CR equal to U, where CL and CR are polychecks obtained from the poly group. And then the detection of an error is indicated by a measurement outcome of 1 on the Ancilla qubit. OK. So now I'll walk you through a very simple example to demonstrate how the QuTracer framework works. So for this, I'll choose the quantum Fourier transform as an example. It's a key component in many basic quantum algorithms. Shor's algorithm, quantum ADA, quantum multiplexer, HHL algorithm, which is about inverting matrices. So on the right side, you see the quantum circuit. So the gate errors and the measurement errors are written in the orange box. So the ideal bitwise distributions are given in green. When you do all the measurements at the same time, the fidelity of your computation is 0.39, which is quite low. So let's do subsetting then. Jigsaw with a subset size of 1, which means 1 qubit is being measured at one time. There are 3 qubits, so there are 3 circuits. You'll get distributions corresponding to each of these circuits. And then you'll combine them via the Bayesian recombination technique to get the final output. Here you see the fidelity improves from 0.39 to 0.57. OK. Now, QuTracer has these built-in optimizations, which further reduces the number of gates for each of these 3 circuits. One of the optimizations is that you basically only keep the gates that impact the qubit that's being measured and remove the other ones. And as you can see, this operation increases the fidelity to 0.71. Also, since you're measuring probability distributions on the Z basis, the RZ gates have no impact and can be eliminated. OK, now we apply polycheck sandwiching. We are using only, we are doing measurements on single qubits, so we can use these poly Z checks. So what ends up happening is that even though the polycheck sandwiching scheme is doing error mitigation, it's doing error mitigation by introducing extra gates. And these extra gates introduce their own errors, and there's a competition there. So the fidelity of the output actually ends up decreasing from 0.71 to 0.68. Now, to fix that, we introduced this qubit subsetting polychecks, where we basically virtually implement these mitigation operations. The theory of this is explained in the paper, but when you do So we have converted those polycheck sandwiching circuits into basically state preparations while using this the state preparation circuit, state preparations. Basically, what we are doing is you have this polycheck, the polycheck circuits, which are given in pink, and you can basically show that the left polycheck can be converted into essentially a bunch of measurements and state preparations, whereas the right polychecks can be absorbed into the observable that you are measuring. The QuTracer framework works like has the following framework. It works with the input circuit. The first step is you analyze and prepare the circuit. Then you do circuit execution and error mitigation. Then you do the global distribution update. And in this whole process, there are lots of optimizations that we can do that depend on the fact that we are basically doing the subsetting technique. There are state preparation reduction, localized gate simulation, gate bypassing, state traceback, fault dependency removal, qubit remapping, qubit subsetting polychecks. All of these optimizations work in the middle, and as you can see in the previous example, the fidelity went from 0.39 to 0.87, which is a huge improvement in the output. So the scaling. Obviously, circuit cutting is being used, and as I mentioned, there's some exponentials there being introduced, so consider you have exponential computation being introduced here. However, if you keep the size of the subsets to 1 qubit, it's manageable, and as you will see, the results that we get are like very encouraging. So for n qubits, m layers, k shots, and a qubit subsize of s, the total number of quantum circuits is order c raised to power s and m. The total number of shots in the QuTracer framework increases linearly with the number of layers in the circuit. Both classical and computational memory overhead scales linearly with the number of qubits and the number of layers. So we performed these some experiments on actual hardware. This one is noisy simulation, but later I'll show you the hardware simulation results. But even in this case, you can see in the first figure, as the measurement error is increasing, every other known similar algorithm basically does much poorly than QuTracer. And as the C naught, which is a 2-qubit gate in a quantum circuit, the number of C naughts increase. You see that the others tend to do less and less well, and the QuTracer framework sort of is doing very well here. And it's almost, the worst one is like 0.88 here, corresponding to 25 C naught gates in the circuit. So we ran these results on actual, we ran the computation on actual quantum hardware, IBM Hanoi device, and IBM, the 27-qubit and the 127-qubit device. And on the left side, you see the different types of experiments that we did. As I told you earlier, QuTracer introduces more number of shots here. But if you look at like the average number of 2-qubit basis gate count, QuTracer is much smaller than Jigsaw and the original circuit, and the fidelity is basically 9 times better than the original circuit and the Jigsaw computation. Similarly, we did computations for like 12-qubit, 15-qubit, and 10-qubit circuits, VQE and QAOA, with 2 and 3 layers. Even though the number of shots in QuTracer are larger, the average 2-qubit basis count is much smaller than original and Jigsaw, and the fidelity improvement is much larger as well. We are working on reducing these number of shots even more by doing LOCC, like local classical communication and mid-circuit measurements, but mid-circuit measurements are not high fidelity, so like right now, we haven't fully implemented that, but these number of shots that you see here can be further reduced down with some more work. Here's the QR code for anyone interested in seeing the actual paper.
All right, please say your name and affiliation when you ask the question.
Hi, I'm Jung Yu, and from University of Pennsylvania. So in your work, you show that there is a measurement on the subset of a total quantum space. Is that right?
Yeah.
Yeah. So I think in your example, you are measure the quantum qubits one by one. So for a 3 qubits model, you have to execute the circuit 3 times.
Yes.
However, do you consider any grouping method, for example, grouping those qubits into subset and measure them?
You can subset 2 qubits, 3 qubits, and
Yeah,
I showed in the scaling. You can do that.
Yeah. Okay. So do you have any evaluation on that method?
We have done 2 qubit subsets in the paper, and I think you can look at that up in the paper.
Okay.
So if you increase the subset size, you basically allow to check both qubits at the same time. So it definitely improves, but it comes at the cost. As you saw in the scalings that I was talking about, the scalability kind of goes exponentially with the subset size. So that's why we kept it to 1, and it also helps us do the poly checks with just like control Z operations and stuff.
Thank you very much. That's a great job.
Thank you.
Yeah, hello, I'm Gokul Ravi from Michigan. So yeah, nice talk. So I have 2 questions. So the first one is, so I think one of the benefits you mentioned in comparison to Jigsaw was I think the reducing the number of subsets. If that was, it seemed like at least that was one of the benefits in your table. So if so, or have you tried implementing this or comparing this with Warsaw, because Warsaw significantly reduces the number of subsets compared to?
No, that's not the advantage. The advantage is like, in this one, we use Jigsaw-like subsetting, but we combine that with keeping track of the state of the qubits via circuit cutting, and also on top, we do error mitigation at the same time. This is not something that's done in Warsaw or Jigsaw.
Okay, so I guess that sort of goes to my second question, which is, so you spoke about like the subsetting and how that relates to the polycheck sandwiching and so on, right? So is there some specific benefit? So it seems like, are you just combining these different techniques, which is still a great engineering effort, or is there some way these techniques are interacting with each other, which make them like?
Yeah, they're all being used at the same time. We use qubit subsetting, we use circuit cutting as like quantum watch points to keep track of the state, and also polycheck sandwiching, which is, I should have cited the paper that we have on polycheck sandwiching, but we can talk offline about that.
Okay, sure. Yeah, okay. Thank you.
Okay.
All right, let's thank Said again.
Hello, everyone. Thank you all for being here today. My name is Pratyush, and I will present our work on serving large language models efficiently at scale. LLMs have exploded in popularity over the past year, with many use cases spanning chatbots, search engines, code completion tools, and so many more. To meet this growing demand, cloud companies across the board are investing billions of dollars into building new GPU clusters to run LLMs. These LLM clusters are very expensive and power hungry. The main reason is that LLMs need a lot of GPU memory, but the memory capacities of GPUs have not scaled in proportion with their costs. In addition, the power usage of GPUs has grown up by 3 times over the past few generations, and it is likely to keep growing in future generations. These trends make it extremely important to optimize LLM efficiency. In particular, it's very important to optimize inference efficiency, since its compute demand far exceeds that of training at scale. The reason is that model training is typically amortized across billions of user queries, and that makes inference the key compute bottleneck at scale. In this talk, I will present Splitwise, which is our technique to improve the efficiency of LLM serving clusters. In particular, I'll show how LLM inference has 2 distinct phases with different resource requirements. Based on this insight, I'll show how Splitwise splits these phases on different servers for efficient resource management. And using Splitwise, I'll show how we can design clusters that improve the efficiency over existing designs across a variety of metrics. Let me get started by diving into how LLM inference works. Let's say you have a user who goes to ChatGPT, selects GPT-4, and then asks it a question. This question is also called the input prompt. The model converts this input prompt into a matrix of tokens, which you can think of as a mathematical representation of words, and it then begins the inference process. The way generative inference works is by multiple forward passes through the model. In the first forward pass, the input prompt is processed by the model, and it generates a new output token and some intermediate memory state. This output token is returned to the user as a partial response, and the memory state, also known as the KV cache, is processed for each of the input tokens sent by the user. To generate the next output token, this KV cache and the newly generated token are fed back into the model so that it can do its second forward pass and generate a new token and some additional KV cache state. This process repeats until a special end-of-sequence token is generated, and that marks the completion of this inference. When doing such inference, users care about a variety of performance metrics, like the time to first token, the time between tokens, and the end-to-end response time. Now, you might have observed that generating the first token is different than generating the rest of the output. This naturally creates two phases within each inference request. The prompt phase involves a compute-intensive operation to process the input in parallel, and it generates the first output token. The token phase relies on memory-intensive operations to sequentially generate the rest of the output. As you might expect, these phases have different resource usage properties. For example, prompt phases easily hit a throughput bottleneck with large batch sizes, whereas token phase throughput continues to scale with larger batch sizes. But if you look at the y-axis here, token phase throughput is actually much less than that of the prompt phase. The reason is that token phase batches are constrained by memory. The graph here shows the GPU memory used corresponding to the number of tokens being processed in each batch. What you can see is that token phase batches use much more GPU memory than prompt phases while processing much fewer tokens. The reason is that token phase batches rely on KV caches, which can be pretty large, and their memory sizes essentially constrains how many tokens you can process in a single batch. Prompt and token phases also have different power usage characteristics. The graph here shows the power draw of three inference requests executing back-to-back. The power peaks here correspond to prompt phases, whereas the troughs correspond to token phases. So to summarize, prompt and token phases have very different properties. Prompt phases are compute and power intensive, whereas token phases are memory intensive, and they benefit much more from batching. So naturally, these two phases, which have very different resource requirements, are inefficient to run on the same piece of hardware. But this is what is done today. Instead, with Splitwise, we propose splitting these phases on different servers, which easily lets us use different batching strategies and power management techniques that are better suited for each phase. In fact, we could even use specialized GPUs in each server since they offer different trade-offs. For example, if we compare the recent NVIDIA H100 and A100 GPUs, we see that the compute capacity has scaled much faster than the cost or the power draw, but the memory capacity has remained the same, and the bandwidth hasn't scaled proportionally. As such, we could expect that A100s might still be reasonable at running token phases. So to show this, we profile the prompt and token phases on these GPUs and plot the ratio of the latency and the cost incurred. A100 is better above the dashed red line for reference, and H100s are better below. As expected, we find that prompt phases are much faster on H100s and even cheaper than running it on A100s. But for token phases, although H100s are still faster, the degree of speedup on them is much less. And importantly, it's actually much cheaper to run token phases on A100s. For running the request end-to-end, we again see no clear winner between H100s and A100s because token phases dominate the execution time of the request. So depending on the performance and cost objectives, Splitwise can choose the most preferable hardware to run each phase. By doing this, Splitwise can better utilize the wide variety of accelerators available on the market, and importantly, it allows future hardware to optimize for each of these phases. While this is great, it has a key challenge, which is that we need a way to transfer this KV cache state from the prompt server to the token server. Splitwise overcomes this challenge by using GPU InfiniBand, which is commonly available in today's clusters. For example, A100 clusters support 25 gigabytes per second between each pair of GPUs, and H100 clusters support double that bandwidth. For large models which are partitioned across multiple GPUs, Splitwise can actually parallelize these transfers, which gives us even higher bandwidth to transfer the KV cache. Unfortunately, this high bandwidth might still not be enough, since KV cache sizes can be very large, like hundreds of gigabytes. Transferring them in a naive manner could still result in a lot of latency impact for the inference. To reduce this overhead, Splitwise overlaps the straight transfer with the prompt phase computation. Basically, since the KV cache entries are populated for each layer in the model, we can start shipping the KV cache right after finishing the first layer in the prompt phase. We evaluated both of these approaches for KV cache transfer. The serialized approach transfers the KV cache after completing the prompt phase, and its latency scales with the KV cache size. The overlap approach significantly speeds up transfers for large KV cache sizes, but it has the problem of incurring overhead at smaller sizes due to synchronization overheads. We designed Splitwise to get the best of both worlds by using a thresholding mechanism based on the input size. Overall, Splitwise incurs less than 1% latency overhead for the typical inference request, while providing many other benefits that we'll see soon. So in the final part of my talk, I'll describe how Splitwise improves inference efficiency at scale. At a high level, Splitwise partitions the servers in a cluster into 3 pools. The prompt pool runs prompt servers, token pool runs token servers, and we have a special mix pool with servers that can run either phase. The reason we need a mix pool is so that we can handle workload variations without much latency impact. A global scheduler is responsible for moving servers across these pools. Servers are typically kept in the prompt or the token pools, but they can be moved into and out of the mix pool with very little overhead. This global scheduler also decides how to assign requests to their prompt and token servers based on the queues at the servers and their memory utilizations. Servers themselves manage queues independently, and they implement phase-aware batching. The general idea is that prompt servers limit batch sizes for higher throughput, whereas token servers maximize batch sizes under memory constraints and SLOs. You can find a lot more details about the cluster provisioning and management in the paper. For our evaluation, we compared cluster designs optimized for cost, power, and performance using 2 production traces from Azure. Our general methodology was to use these production traces to drive characterization on real hardware, and we then use these profiles to drive cluster scale simulations. For our baselines, we use separate A100 and H100 clusters that run requests end-to-end on the same server. For Splitwise, we had 2 options. Homogeneous Splitwise uses the same server type for both prompt phases and token phases, whereas heterogeneous Splitwise uses or tries to use H100s for prompts and A100s for token phases. In this talk, I will only show a subset of the results, and there are many more results in the paper. First, let us look at the results for throughput-optimized clusters under a fixed power budget. All of the results are normalized to the baseline A100 cluster. Here, we find that homogeneous Splitwise supports about 2.4 times higher throughput compared to the baseline cluster while using exactly the same resources. This throughput increase is enabled by the phase-aware batching that Splitwise adopts. Heterogeneous Splitwise further improves the throughput at slightly higher costs while using fewer servers. Next, let's look at cost-optimized clusters under a target performance requirement. Here, both the Splitwise variants offer the same performance at much lower cost than the baseline cluster. Further, heterogeneous Splitwise uses fewer servers and lesser power than the homogeneous variant. Overall, splitwise clusters offer much better trade-offs than existing designs, and they considerably improve inference efficiency at scale. So to summarize, LLM inference requests have distinct prompt and token phases. Splitwise split these phases on different servers to enable better resource management. And as a result, inference clusters designed using Splitwise have much higher efficiency than existing designs. If you're interested in learning more, I encourage you to check out our paper. We've also released our code and traces. Thank you so much for your time and attention.
Questions, please, go ahead.
Hi, I'm Womam Lee from Seoul National University. It was a very interesting talk, so thank you. And my question is, it seems like the provisioning is very important in Splitwise. And as the models become capable of processing millions of tokens, and the variance between inputs can be significantly large. So the statically setting the number of prompt machine and token machine can still benefit in the era of millions of tokens?
So there are, I guess, two ways in which Splitwise could deal with that. One is you could use homogeneous Splitwise in such cases, in which case you don't need to separately partition prompt and token servers. And if there's a change in workload distributions, the scheduler can just move those servers between the prompt and token pools of servers. But for heterogeneous Splitwise, it becomes a bigger problem because now you have partition prompt-specific and token-specific servers. In that case, you can still perform inference on mixed servers if needed. And on longer timescales, you might be able to change the distribution of your cluster because given the workload being very important, servers are being changed on a relatively regular basis.
Thank you.
Thank you for the wonderful talk. This is Tushar Krishna from Georgia Tech. My question was actually going to be the same about load balancing, but you answered that. So let me ask you one more. I'm curious about, so you mentioned the KV caches get transferred between the two servers. So is that transfer, do you see that becoming a bottleneck for any model sizes or context lengths?
So currently, like looking at the trends with network InfiniBand and like optical networks in other cases like TPUs, these interconnects are actually growing faster and faster. So if it's basically a battle between like how fast or how quickly the KV cache sizes grow and how quickly the networking sizes grow.
So in your case, what was the interconnect? I'm curious. Was it just a regular PCIe between the two servers, or?
No, in our evaluations, we use InfiniBand between these GPUs. You could, if your servers were located in an NVLink cluster, you could also use NVLink, and that's even faster. So this is like slightly worse than the NVLink case.
Thank you.
So, sorry, we don't have time for any more questions. Let's thank the speaker. All right, the next paper is from ETH Zurich and Zentel, Japan. And the speaker is Michele Marazzi. He's a PhD student at ETH Zurich, where he's looking at DRAM security with a focus on raw hammer attacks and mitigations. With this work, he looked at inside modern DRAM chips to reverse engineer the deployed circuitry and understand how research should be evaluated with more fidelity. He's currently on the market for a job industry. For an industry job.
Okay. Thank you for the introduction. So welcome to the presentation for HiFi-DRAM or high-fidelity DRAM research. I'm Michele Marazzi from ETH Zurich. So when we talk about DRAM, probably many of you think about these DIMM modules that you plug in your system, right? But they're made of many DRAM chips. And if we look inside one chip, you will see these banks repeated, where your data is actually stored, and a logic pad in the middle. Now, the logic pad handles logic operations, and we will focus on memory today. So if we zoom inside the bank, we will see this math structure repeated many, many times. And that's where your data is. So let's zoom once more. What do we find? We find the capacitors inside the math, right? So a capacitor can only store 1 or 0, 1 bit of information. There are also rows to select which data you would like to access. So the capacitor can only hold a very, very small charge. So whenever you want to interact with it, you need to go through the sense amplifier, this element connected to it, that it will read and amplify the value for you, like this. But in reality, every single time that you want to interact with a new row, you will have to activate all the sense amplifier in that row. For this reason, sense amplifiers are extremely important for research. They have a key impact on performance and power of DRAM. There are many research projects linked to it, mainly processing in memory, but also security, for example, for hammer mitigations, and optimization that try to improve DRAM speed. So it feels very natural to ask the question, OK, how is this block designed? I mean, after all this year of research, we should know by now, right? Let's look at literature. We look at literature, what do we find? Many repeated kind of backgrounds with same references and kind of similar assumptions, right? There's also one book from 2008. So the answer is that before HiFi-DRAM, we didn't really know exactly. So if you were a researcher, you had a really, really cool idea, and then you would look at a modern device, and then you would have no clue if your idea would fit nicely, if it would integrate nicely with the circuit, because on their side, industry basically disclosed nothing about the deployed circuitry. So in the end, what a researcher is forced to do is to rely on assumptions. For example, relying on a circuit that might be 10, 20, 30 years old. So the question is industry really still using circuit that is old? We will see with this presentation that forcing researchers to rely on assumptions has created a very big gap between industry and research. So how do we look for sense amplifiers? Well, we know they're somewhere inside there, right? So we take the chip. It's covered by a kind of plastic coverage, so we use sulfuric acid to remove it. We decap it, basically. And now it's where the challenges really start. Because imagine the chip may be long 1 centimeter. You would need to zoom 1 million times to get to the size of the feature of interest, which are 10 nanometers, extremely small. And you cannot do this in an optical way. So you need to find a different way to image these features. And what we used was scanning electron microscopy, or SEM. Now, this machine is based on throwing electrons at your sample and looking how they bounce off, how they reflect. And there is a problem, though. It's extremely expensive, and it has a very, very small field of view, which means that if you acquire for 24 hours this chip, you will get a negligible part of it. So you need to be extremely careful in understanding where you want to image, right? You need to be extremely careful about understanding and finding the region of interest. So how did we do that? Well, remember at the beginning I showed you this in the background? Well, a DRAM vendor wants the majority of the chip to be capacitor. It wants a really, really high yield, right? So we said, OK, mats are everywhere, almost in banks. So let's look there, right? We do a blind acquisition. There is a small, small problem, and it's that mats are not only surrounded by sense amplifier, which is our target, but also by row drivers. Now, row drivers are quite smaller than sense amplifiers, so we can distinguish across them. They also have a quite different functionality. Basically, they activate the row you want to access, right? So for example, we start acquiring in one direction, blindly. And at the beginning, probably, we will only see capacitors. And as we go and go, eventually we might find the logic, right, a circuitry. And in this case, for example, it's the row driver. And we can identify that it's the row driver because we pass quickly from one mat to the other, right? So we know we had the wrong direction. But is this a really big problem? No, because we just repeat the acquisition in a perpendicular way, right? So at the beginning, again, maybe we see capacitors only, but then eventually we will get our sense amplifiers, right? Good. So is that it? Not really. Because integrated circuits are made of many, many interconnected layers, right? So probably many of you have studied electronics. And when you were studying electronics, maybe you used a white breadboard, right? You connected your elements, and you could take a picture from the top of that, and it will give you the entire circuitry. But this is not the case for ICs. ICs are many interconnected layers, right? So you need to perform a 3D reconstruction of your region of interest. And how can you possibly do that? Well, in the same machine as SEM, often there's also FIB, or focused ion beam. What focused ion beam allows you to do is to carve out material from your region of interest. And what we used FIB for was basically to cut off slices exposing cross-section of the region of interest, which we then image through SEM. And we repeat this for the entire region of interest, right? We get many, 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 many slices. But these slices are extremely noisy, and they move, and they have a lot of drift. And again, the feature of interest may be so small that they are 100 times smaller than the slice size. What does this mean? It means that we need to be extremely careful about filtering and aligning these slices. And after we've done this, we can actually conclude the processing. And we repeated the processing for 6 DDR4 and DDR5 chips, right? So 3 DDR4, 3 DDR5 chips from the 3 major DRAM vendors. And this is the result of everything I showed you so far. So this is the first public image of modern DRAM. This is a DDR5 sense amplifier structure produced in 2022, so state of the art. You can see the capacitors where your data is stored, and they are connected with wires called bit lines to the sense amplifiers. But we can also look at layers, right? Maybe it's a bit easier to identify structures. So there is the bit line layers. Basically, these are wires, right? And then there is the transistor with the gates and contacts. And then at the bottom, you also have these transistor active regions. So is this over? No, we still need to get the circuitry, right? So we still need to do a lot of work to actually get information out of it. And how can we possibly do that? Well, we need to understand how on the same layer things interconnect, but also how they interconnect across different layers. Remember, they are ICs. So let's keep as a reference this cross-section, okay? There we go. So we keep it as a reference. And in theory, we should map the entire block, okay? But for simplicity, let's look at a very small part. And what we do is that we start at the top, right? So what do we find at the top? We find a shared wire. It is a very big wire. It's typical in ICs. It's probably a power line, right? And we draw in our circuit reconstruction. But remember that ICs are these interconnected layers. And how do they interconnect? They interconnect via a connection called vias, right? In the middle, you see, it's like vertical connections. So we start from a shared wire, and we need to follow it, how it goes downwards, right? So we see that there are vias underneath. We follow them, and as we follow them, we find new elements, new wires. And because they are close to the circuitry, we also need to map them, right? So we add them to the circuit reconstruction. And we go, and we go, and we go, and then eventually maybe we find the transistor, and these wires connect to the transistor, so we draw them as well. And because we know where the capacitors are and where the bit lines connecting to the capacitors are, after we have repeated this procedure many, many times, we can infer how the circuit looks like. So our first insight is quite interesting. If you look at literature, there's always one big common assumption, and it's that there is a classic circuit topology, the classic sense amplifier circuit topology. Probably many of you know about it, and unfortunately, it has been replaced in half of the studied chips, right? It has been replaced by an offset cancellation design, which is more complex. It adds new transistor, new sense amplifier events, and the idea is to enhance the reliability for smaller technology nodes and denser designs. So this could open a research direction where we port existing literature to this new architecture. Then we looked at 10 years of DRAM research, and we tried to understand, do they share inaccuracies of wrong assumptions, and how would look their overhead on modern devices? So how would they look on DDR4 and DDR5 devices? So we found one inaccuracies, for example, some papers assume they can add connection in this layer without requiring overhead. But this is unfortunately not possible. There is no free space. Another is considering extra element to be deployed where that's not really the case, like these extra transistors. There are a few more. You can check the paper for the details. The important thing is also that no paper ever considers this type of design, right? So what happens when we include all these inaccuracies and we try to understand, okay, how does the overhead look like on modern commodity devices? Well, what happens, unfortunately, is that we find overhead errors up to 175 times the original estimations. And this is shared across the majority of papers. 8 out of 13 have errors above 20 times. So again, future research direction, implementing the original paper's ideas, but in different ways, that maybe they more easily accommodate commodity devices. We also looked at transistor sizes. If you want to simulate your architecture, this is very important. I will go briefly here. We measured each transistor from each chip. We ended up with more than 800 individual size measurements. And compared to the available DRAM model, unfortunately, they are very, very inaccurate, up to 9 times. They're very optimistic, and neither consider offset cancellation sense amplifiers. So another research direction, improve the fidelity of analog models and then reevaluate past simulations, because maybe we are losing some kind of trade-off that is interesting to look at. So to conclude, we reported circuit topology, transistor dimension, layouts from modern DRAM, which was all previously unavailable to researchers. We identified overhead errors up to 175 times and multiple major inaccuracies in past research. But to improve the fidelity of future research, we made everything that we extracted open source. Thank you.
Questions?
Hi, Michele. Stefan Soroy from Microsoft Research. This is fantastic work. So I have a question that you might or might not know the answer to. At which point do you think the research community diverged or the industry diverged from the assumptions that the research community have made? Do you think that started with DDR4 or it was as old as DDR3 or DDR2?
Thank you. Thank you so much for your question. So if we look at the circuit used, we already see this discrepancy for a specific manufacturer already in DDR4. So already for DDR4, there was a discrepancy. It's harder to tell for DDR3, honestly. We don't know about this.
Okay, so for one manufacturer, you saw it as earlier DDR4,
Yes.
but for the others, you didn't.
In one case, the manufacturer passed from DDR4 to DDR5 using a different circuit.
So that seems to suggest that they're more recent, maybe.
Well, DDR4 production.
Yeah. Okay, thanks.
Thanks.
Rakesh Kumar, University of Illinois. So if the message is that data and models in academia are not quite accurate, that's something you've heard before. What I'm curious about is, are there ideas that are well acknowledged to be good ideas in our community that now with this metrology that you did, you'd say are not good ideas? Alternatively, are there ideas in the community that are well acknowledged to not be good ideas that your metrology suggests would actually be good ideas?
Yes, so thank you for your question. Well, whether an idea is good or bad is not really up to me to decide. I think what the community needs is a method based on something real to evaluate what the community thinks is good, and it should also understand what is exactly the measure of reference that we want. Is it the area overhead, or is it the functionality that you want to implement? I think the impression I had so far is that the DRAM research focused a bit too much on the area overhead. So a lot of these works tend to not consider too much the functionality aspect or the novelty aspect, but try to reduce as much as possible the overhead area. And what happens is that it then this clashes with modern commodity devices. Then the idea may become strange to look at, right? So I think it's two things, right? We need to see that maybe to improve DRAM with, for example, processing in memory, you're not going to do it with less than 1% overhead. And maybe this is fine, right? But this is a shift in the way we perceive DRAM research. Thank you.
All right. Let's thank Michele. The next paper is from NVIDIA and MIT, and the speaker will be Jenny Huang. Jenny is a research scientist at NVIDIA. Her research interests are architectural design space exploration to co-optimize hardware, mapping, and algorithms. Before joining NVIDIA, she earned her PhD in computer science from UC Berkeley.
Thanks for the introduction. Good morning, everyone. Today I'll be presenting our work called Mind the Gap, Attainable Data Movement, and Operational Intensity Bounds for Tensor Algorithms. So imagine you're the lead designers that are given the opportunity to architect the next generation AI accelerators for a new tensor algorithm called GPT-X. So you're presented with this chip area of 800 square millimeter and the best available DRAM from the vendor. You're free to fill this chip with either compute resources or on-chip buffers to optimize for performance. And now you'll be facing a key design challenge, which is how do you provision the chip area between the storage and the compute? So a straightforward solution would be to perform a design space exploration. However, if you look at the size of a typical architectural design space search, together with the mapping search for a design, and a fairly reasonable time to evaluate each implementation, it would take trillions of years to go through all of these designs. And as a result, this process is typically very time-consuming and costly. But without exhaustive search, we don't know if our design is optimal or how far it is from the optimal. So consequently, there's very design insights we're able to draw from this process. As an alternative, we can turn to the roofline model analysis with the speeds and feeds calculation to develop fast design intuitions. So this analysis is typically carried out using the algorithmic maximum operational intensity, which can be calculated as the total compute of the algorithm divided by the algorithm minimum data access count of the algorithm, which is simply the sum of all the operand sizes in a tensor algorithm. And by looking up the roofline model using this operational intensity, we can decide whether to add more compute resources or increase the DRAM bandwidth to enhance the performance. But wait a second, there's really no consideration of the trade-off between the buffer and the compute capacities in this analysis. So now it seems we're kind of running out of tools to help us quickly identify the optimal buffer to compute ratio on chip. However, if we take a step back and think about what's missing from the previous analysis, it might have occurred to you already that the workflow rarely operates with algorithmic minimum access count or the optimal operational intensity. So here is an example of actual backing store access at different memory levels of a GPU for a matrix multiplication kernel. You can see that they are all larger than the algorithm minimum data movement count. And this discrepancy arises because that the actual backing stores and operational intensity would depend on the mapping and the buffer sizes. So in order to look at the impact of mapping and buffer sizes, it would be nice to have a diagram looking like the one on the slide for each target tensor workload that could be expressed in ISAM notations. So in this diagram for a GEM workload, the x-axis represents the buffer size, and the y-axis is the amount of traffic to the backing store that's achievable with any mappings. So for all the cache experts in the audience, this is not a missed curve, as it is not derived from a single mapping implementation, but many Pareto optimal mappings that exploits data reuse. And we refer to this curve as the ski slope diagram, as the data movement monotonically decreases with the buffer size increase. And with this diagram, we're now able to answer a few important architecture design questions for tensor algorithms. The first question is that, given a buffer capacity, what is the minimum attainable data access count? And as demonstrated with the gap 0 and the previous example, this number could be orders of magnitude away from the algorithm minimum number. And the second question is, how much buffer capacity is required for us to achieve this algorithm minimum data movement? And as demonstrated with the gap 1 on this diagram, we don't actually need to buffer all the operands in order to achieve this minimum data movement. And we can use this diagram to tell us how much buffer size we need in order to enable full data reuse. And the final question concerns how the workload benefits from an incremental increase in the buffer size, which can be addressed by examining the rate of change of this curve. And now I hope I have convinced you that the ski-slope curve provides valuable design insights. This brings us to our contribution and approach to efficiently generate these ski-slope diagrams. So we call this approach our genesis, which stands for mountain creation, and mirrors our efforts to create these ski-slope diagrams. And how do we create these mountains in a practical way? So first, we will need to have a tractable mapping space so we can find the best mapping. And second, we want to further reduce the search space by avoiding separate mapping search for every buffer size. So instead of performing a exhaustive mapping search on the real design, our first approach is to have a simple two-level surrogate architecture called the Snowcat with unlimited buffer capacity. And the simplicity of this architecture enables this exhaustive search. At the same time, we want to ensure that this architecture provides a lower bound of data movement that's achievable by any real designs. And in order to avoid the separate mapping search for every possible buffer capacity, as the second challenge, we use the following methodology. So given an input tensor workload defined in ISOM notation, we perform an exhaustive search on the Snowcat architecture with unconstrained buffers. And for each mapping, we will gather the data access count and use the buffer utilization of each mapping to represent its buffer capacity requirement. And the ski-slope curve is the Pareto optimal frontier of all these mapping points. So once we have derived this data movement bound in the ski-slope diagram, we can simply take its inverse and multiply it by the total operations in the algorithm to produce our operational intensity bound. And now let's look at some example orgenesis analysis. So here we have 3 different gems with different shapes. So each of them is labeled with 3 numbers representing different sizes of the dimensions. So here are the data movement bounds and operational intensity bounds we obtain for these matrix multiplication kernels. And we can see that different shapes result in different slopes in the ski-slope diagram. And we have a bunny hill green curve for the smallest gem, and a blue curve for a medium-sized gem, and a black diamond curve for the gem with largest tensors. We also observe that these bounds all decrease in a power law manner. And by carefully examining the operational intensity bounds, we also had a very interesting findings, which is that the maximum effectual buffer size of a matrix multiplication is approximately the size of its smallest tensor operand. So that means in order to fully reuse the data in our multi-member hierarchy, we only need to buffer the smallest tensor in a gem. So with this, we show that our genesis can produce bounds that reveal powerful design insights. And besides a single tensor operations, our genesis can also take a chain of operations as input. And with that, fusion is an optimization we need to analyze because it further reduces the data movement bounds for a chain of operations by eliminating the backing store access of the intermediate outputs. Note that fusion also imposes extra intralayer mapping constraints because not all combination of the producer and the consumer operation mappings are compatible. So with this, we're able to create the ski-slope diagram for a chain of 6 operations in a large language model block. So we have this purple curve showing that the baseline with no fusion implementation, and the green curve for a fused implementation. So we find that the fused implementation does not always outperform the unfused ones due to the extra mapping constraints imposed in the intralayer mapping space. And it is only beneficial when the buffer size is large enough to enable both intralayer and interlayer reuse. So this analysis showcased the capability of Orgenesis in comprehending complex optimizations like fusion. So now that we have a way to understand how the buffer size impacts the data movement and operation intensity, what we really need to do is we need to understand how this buffer size impacts the performance in order to answer our initial buffer provisioning question. And here's the way of doing it. So first, we can look up the operational intensity, attainable operational intensity from our operational intensity bound diagram using the buffer size as input. And next, we can plug in this attainable operational intensity into the roofline model, along with the hardware flops and the DRAM bandwidth to produce the performance projection. And if we combine these two models together, we can craft our final performance model, which with buffer size as the input and the peak through performance as the output. And assuming unlimited compute resource on chip, by using this buffer-based performance bounds and the corresponding chip design specs, we can construct a performance model that is a function of buffer area ratio. So we see that the performance increases as the buffer size increases because larger buffer reduces data movement. And likewise, we can construct a compute-limited performance bound, assuming we're only limited by the computing resources. And this decreases linearly with the buffer area ratio increase. And combining these two curves together by taking the min of them, we can produce a mountain-like performance bound with respect to the buffer area ratio. So when the ratio is small, the workload performance is limited by the memory bandwidth due to the high volume of data movement. When the buffer gets large, it starts to be bounded by the compute resources. And since this curve is concave, we can quickly pinpoint the optimal buffer area ratio and use it to answer our design questions for resource provisioning between storage and compute. So this case analysis demonstrates that Orgenesis can complement the roofline model and provide a buffer size suggestion. So to conclude, Orgenesis presents a radically new design space exploration approach for early stage exploration. It offers visualizations and insights for design trade-off through the ski slope diagram, and it could be a powerful add-on to the roofline performance model. So if you're interested in learning more about our work, please drop by our posters and check out our project from the link below. Thank you.
Any questions? Let me ask a question before somebody. Can you tell us a bit about the limitations of the model?
Limitations of the model. So currently the model does not, so in this paper it does not address the parallelism bound. So parallelism will introduce more buffer copies. So we are not considering that. But, and then we are not considering a sparse workload. So we cannot comprehend the data movement bound for a sparse workload if it's optimized. Yeah. So these are the key limitations. Yeah.
One question.
Good talk. My name is Socrates, and I come from Cornell University. I'd like to ask a question regarding when you have some kind of workload that's both dependent on memory loading and computation at the same time. In such workloads, sometimes it is, say that you have huge memory, and it's not limited by the memory buffer size, but say the bandwidth or the sustained amount of stuff that you have in the interaction process during computation. Say that you're doing some kind of convergence problem. In that case, how good does this model hold?
So as long as the workload is statically analyzable, I think even though if the workload is like just bandwidth bound, we should be able to produce a fairly accurate data movement bounds. For example, like in that case, basically that means when we increase the buffer size, we wouldn't necessarily reduce the data movement if there's no reuse in the algorithm.
I think my question is if it's not statically analyzable, like a convergence problem, where you need the stages of one to compute the other. So that you need your data needs to be there before you can compute.
Oh, so, okay, that's a great question. I think we can probably do some overlapping, if that's one possibility. And the other things, you can do some fusion. So, and this also only provides a bound. So it's not like we will address all those detailed dependencies in this. So basically, it will be a bound for those detailed dependency we need to account for in this case. Yeah, does that make sense?
I understand. Okay. Thank you.
Quick question.
Yes, I can see how you can move from a kernel, like a gem, to a more, to this study, but how you move from a dynamic kernel that on a SoC you have multiple functional units. Like I can see just how you can do it for gem, but I cannot envision how you can do it for a large SoC and a dynamic kernel.
Oh, that's a great question. So I think the solution there might be to turn to some hierarchical solution, right? So basically, you can analyze the statically analyzable part with this bounce, and then you can still dynamically compose your dynamic bounce using this bounce with some other outside loop controllers. That answers your question?
Yes,
but that's a great question.
Yes,
yeah.
Thank you.
All right, let's thank the speaker again. Last talk is from Shanghai Jiaotong University and a few other universities from China, 3 more. And the speaker will be Tongxiao Xu. Tongxiao is a second-year graduate student at Shanghai Jiaotong University, and his main research area is energy-efficient edge computing.
So good afternoon, ladies and gentlemen. I'm Tongqiao Xu from Shanghai Jiaotong University. It is an honor for me to present our work, A Tale of Two Domains, exploring efficient architecture design for truly autonomous things. So this work is advised by my Professor Chao Li and Ming Guo. In this talk, I would like to introduce our methodology as well as a platform, Chrysalis, for designing efficient autonomous things. So I would like to introduce our topic from 4 aspects. Let's just start with background and motivation. So in the current decade, our human is dealing with various tough but important tasks, including pandemic analytics, wildlife observation, disaster monitoring, and so forth. In the past, these tasks can be difficult to be complete without human labors and high costs, while the AIoT devices have the potential to help humans in these various tasks. So they can perform more difficult tasks than ever before, and the key feature of AIoT is that they are tiny devices capable of transferring energy to cognition. By diligently collecting data from the real world, the AIoT devices are capable of providing humans with semantic information. And with the development of AI technology, the AIoT devices can be very intelligent and perform more difficult tasks than ever before. So, however, the bad news is that present AIoTs are unprecedentedly high maintenance. So it is because they rely heavily on the external resources. So for inference, there's a cloud in the loop, which means the cloud should help the AIoT devices in the neural network processing. For the energy, there's a power supply in the loop, which means the AIoT devices are powered by the power grids. So this leads to increasing cost on cloud and energy, limiting the deployment and expansion of AIoT for the future. So this leads to our consideration. We think that the next generation of AIoT should be autonomous things, or AUT. From the perspective of architecture, the autonomous things should realize both inference autonomy and energy autonomy. The inference autonomy refers to the ability of performing in situ inference to be free from the cloud, and the energy autonomy refers to be powered by the energy harvesters to be free from the power grid. The 2 domains lead to one tail, which is what we need for the future maintenance-free and sustainable AIoT architecture. And next, I want to show you that the autonomous things is not just existing in our imagination, and researchers have made efforts in relevant fields through decades. And the year of 2005 is the starting point of energy autonomous system, Helio mode and Trio were two seminal works focused on the energy harvester-based sensor nodes. On the other hand, the inference autonomous system has become a hot topic since 2015, and multiple researchers focus on topics such as dedicated accelerator support or DNN data flow analysis. In recent years, we started to focus on the autonomous things, which is the energy autonomous and inference autonomous system, EA and IA. We find that although there are works focused on EA optimization or IA optimization, there's still a lack of holistic design methodology by considering EA and IA co-optimization. It is very important, and I want to show you that it is because the skill mismatch may occur between EA and IA. And this diagram shows some of the worst cases of the designs with extremely big energy harvester and weak inference device. Most of the harvested energy will be wasted, while with extremely weak inference device but big energy harvester, big inference device, the AUT will suffer intolerable latency on harvesting energy. This diagram shows an easy version of the issue, but the one-dimensional scale cannot describe either of the subsystems, and when we dive into the architecture, we also find it non-trivial to do AUT holistic design because huge design dimensions exist in hardware and software. For some specific examples, in the hardware design space, even the size of the capacitor should be decided and may have the direct impact on the performance. For the software design space, the neural network data flow should be decided from hundreds of thousands of mappings. So when dealing with holistic design scenario, we're actually composing this design space together into a huge one. It becomes difficult for us to decide which is the better choice for autonomous things because of the multiplicative effect in design space. And this leads to the designs of ours, the holistic design methodology, which is Chrysalis. And generally, we deal with or address 4 key issues existing in AUT design. For architecture and system, we consider how to model AUT and deal with architectural diversity and temporal complexity. For environment and workload, we consider how to optimize the autonomous things and consider various external scenarios and huge internal design space. So we solve these 4 key issues by the Chrysalis consideration of the components, and we actually, this figure shows where we address these 4 issues, which I would like to introduce in detail. So let's just start from AUT modeling. So first, we support architectural diversity by providing component-based describer instead of a single simulator. We focus on the description of each component of autonomous things in the describer, and by providing the general models, and based on general models, we also provide the customized descriptions with state-of-the-art simulators to simulate the components as accurately as possible. And secondly, to overcome temporal complexity, we propose step-based simulation, and the step-based simulation is monitored or activated by the Chrysalis evaluator. The components in the describer should update the state in the simulation on the timeline, and the evaluator will track out some of the critical data which will be used in the target function for the search. So thirdly, for AUT optimizing, to satisfy the various external scenarios, we propose comprehensive evaluation, and the users are able to specify the deployed environments of autonomous things and the design objectives, which is the target function for the search. So in the evaluation process, the designs are evaluated in each given environment with the target function to show the overall performance of the designs. So finally, to address internal huge design space, we propose bi-level search methodology, including the hardware level and software level optimizer. So initially, for the search, the hardware level optimizer will generate a hardware configuration and employs it as a starting point for the software level optimizer for the data flow search. This narrows down the design space because one hardware requires to execute multiple layers in one network, and each of the layers requires a data flow. So with bi-level search methodology, we are able to search the data flows independently. Secondly, I want to introduce the artifact and the evaluation of our work. So by composing the design points together, we have the artifact of our work, Chrysalis. So its name is actually originated from the sentence of Charles Dickens, the famous English novelist, as well as the author of A Tale of Two Cities. He said, "I only ask to be free, the butterflies are free." So butterflies are what we think autonomous things would be like in the future. Like butterflies, AUTs are graceful devices free of cloud and energy. So the word chrysalis means the pupa of the free butterfly, and our artifact can also be considered as the pupa or designer of the free autonomous things. So the next slide will clarify how chrysalis works in detail as a whole, and with constraints, workloads, and objectives. The describer will first generate an overall AUT model, and it will cause the explorer to start the search. The explorer generates a configuration each time and causes evaluator to simulate with the help of the describer's model. It does analysis and returns the result back to the explorer. And these steps will continue in several loops. Finally, we have the output, which is the ideal AUT solution, including hardware and software configuration. We did 2 experiments to show our capability of Chrysalis. And first, we optimized existing autonomous things with Chrysalis to show its rapid prototyping capabilities. So based on the search result, we also built an actual system for the latency testing. Based on the experimental results, we find that Chrysalis effectively simulate and improve efficiency in overall system. And secondly, we utilize Chrysalis to design future autonomous things with AI reconfigurable accelerators. So based on the result, we find that Chrysalis consistently outperforms other methodologies under various conditions. These improvements enable the architecture to make it feasible in the real-world scenarios. So finally, I want to introduce the vision and conclusion of our work. And here's the vision, our consideration of the important design dimensions of autonomous things. We hold the view that energy autonomous systems should adapt to the environment, optimize energy utilization, and consider scalable energy harvester. The inference autonomous system should be aware of application, optimize inference performance, and consider reconfigurable accelerator. By energy autonomy and inference autonomy collaboration, we are actually moving towards efficient autonomous things. In conclusion, we embrace autonomous thing, which is emerging as a maintenance-free and sustainable AIoT paradigm. Chrysalis is an AUT holistic design methodology that first considers the relationship between EA and IA. Chrysalis automates the generation of ideal AUT designs tailored to various application scenarios and constraints. By leveraging Chrysalis, researchers can unlock the potential of AUTs to revolutionize a wide range of industries and domains. And finally, I want to mention that Chrysalis artifact is currently available on GitHub. We welcome any exploration and modifications based on our work. And that's all for my talk. Thank you for listening. If you have any questions, feel free to contact me offline and online. Thank you very much.
Any questions?
Hi, I'm Angshu from NVIDIA. I have a question about your decoupled hardware design space search and the map space search for each architecture. How do you, if you decouple those two processes, for every hardware design, how do you know if design A is better than design B if you're not optimizing your algorithms for each of those designs?
So the question is how to transfer one hardware into another hardware when we are evaluating different configurations. Is that true?
Well, no, you're comparing two hardware designs, right?
Yes.
You want to answer if A is better than B, but the way that we know how to do that is you run a map space search on A for all of the mappings of each workload on A, and then you run a map space search for B, right? And so that composes the design space and map space searches, which is a problem because the search space is too big. But what I liked is what you said, that you separate them, right? And you decompose them. But then the question is, how do you know if A is better than B?
Okay, I think it is our designs of the description or describers component is dealing with such problems. We have the specific models for each hardware for different configurations, and when we are searching, we can transfer different hardware models or simulators, state-of-the-art simulators, to simulate, and we actually build two simulators for different hardwares. So we are also able the expansion of the simulator with our description search. I don't know if I have answered your question.
No, thank you.
Thank you very much.
Okay, quick question. Yeah, Karthik Swaminathan from IBM Research. So what if there's a sudden change in your energy source, like your solar energy, if there is, and does that require a complete reconfiguration, redesign of your hardware with the change in energy source? How closely are the two correlated, and how much wiggle room do you have in the hardware to reconfigure things online?
Okay, our design space is, for the first experiment, we actually didn't change our design space, our hardware of the inference device, but for the energy harvester device, energy harvester subsystem, we have to change the size of the energy harvester, which is a solar panel, and as well as the capacitor, which is for intermittent computing or storing energy for the computing. And for the second experiment, we actually change our configuration of the accelerator. The accelerator is reconfigurable, so you can change the number of processing elements as well as the cache for each element for the search. So this is our design space.
Yeah, but can those be done online? Like, these are things that can change, like the energy source, the magnitude, amplitude of the energy source, say the amount of sunlight to receive, that can be something that change in the field. So once you have come up with a particular design, how do you reconfigure something in the field? Is that something you have considered?
The question is...
Reconfiguring the field. Do you reconfigure in the field?
Reconfiguring the field?
Reconfiguring, how do you reconfigure the design, the inference design in the field based on a change in the energy design, in the EA design?
Okay, it is actually changed with by changing the descriptions, and actually you have to specify what is the configuration of your hardware, and we haven't. It is out of our scope to consider two different separate hardwares for the same inference. So.
Okay, thanks.
Thank you very much.
Let's thank the speaker, and you guys have lunch now in the other room. Thank you.